Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about aerogel. So let's dive right into it. Well, first we have to understand what the heck we are talking about. We are talking about lightest solid known to man so far. What does that mean? That simply means if you take 1 cubic meter of this is almost as same weight as air. It's like practically a zero weight, so to say. So it's very lightweight. Like fundamentally speaking, if I put a block of it in your hand, you will not be able to feel it. It's that freaking light. It's very light. Now this was made by Samuel Krinster in 1931, so it's an old technology, and the story behind it is surprisingly hilarious and mind-boggling because this was done as a bet. There was a bet that take a gelatin or jello and remove liquid from it, basically water from it. Now you may think that simply means drying it. Here's the deal: the moment you dry it, the water rushes out. The moment water rushes out, it destroys the structure that was behind. So a gelatin is mostly a semi-solid kind of scenario where you have liquid that is acting as like a balloon kind of structure, and there is a structure behind it which is very light. Like that's why it's a very what we'll call flexible, so to say. So it's there, but problem is the moment you remove anything resembling the inside, so liquid, it collapses it. So problem with that is like you cannot make a material that has the same structure as that without having water in it or some sort of liquid in it. So that was the better: remove the liquid from the inside without collapsing the structure. Removing liquid, super easy. Without collapsing the structure, that's a new material. Now this gentleman achieved that. So what does that mean? That inherently means we ended up with best thermal insulator known to man. Now be mindful, I'm talking about thermal insulator, not electrical insulator. In some designs you can make them very conductive also, and sometimes have been used inside supercapacitor. So be thoroughly aware of that. Now thermal insulation, why the heck it's so awesome in thermal insulation? Simply because every small gap that it has, it's in nanometers, so to say. Not nanometer, micrometers. So you have 4 micrometer, 8 nanometer, 10 nanometer kind of pockets. Now these pockets trap air because we are in an atmosphere. These trap air. Now because of the structure, because of the chaos, because of the size difference, air cannot go through. So even though air is a very good conductor, that's why you can set up a fire and feel its effect. It's a very good conductor. When you are trapping it in such a small volume and like it cannot conduct to one to another to another to another, it flat out becomes the best insulator known to man. And especially if you are dealing with something, let's say below 1000 degrees Celsius, flat out you cannot go through it. The only limiting factor is that what happens at the structure. Basically that structure is a limiting factor. If you exceed, let's say 2000 degrees Celsius, the structure will get destroyed. So at that point it can't protect you. That's why it's not used as a return heat shield, but you get the point. So flat out the best insulator known to us for convection kind of heating, basically where you have thermal energy converted through hot gases. This puppy is like, I got this, it will not bother you. That's awesome. Now this is a category of product, be very aware of. That's why same way we say nanotechnology does not mean anything. It's just like there is a category of product that comes inside that. Same goes with here. People have made it with carbon, people have made it with silicon. There are other mixtures also, so be mindful. It's a category of product, not one product. Now, what is this structure that we are talking about? Well, if you take a microscope and look inside a human bone, you will notice something like this. Basically, it's a hollow structure. Now, that structure is not hollow as in hollow. There is also liquid fluids, blood, and all that jazz there. So that's the main game. Somehow get this structure out without collapsing it, so to say. Now that mesh is generally the basically wall, the structure, the chaotic structure that we are talking about is made out of long polymers. So generally people prefer things that can make long chains like silicon or carbon. Now removing liquid is the main issue. Every Tom, Dick and Harry, the moment you research this puppy, that's the whole goddamn thing. Remove the liquid without collapsing the aerogel structure. That structure is the aerogel. Once you remove the liquid and once a normal air fills in the gap, you have awesome insulator. But you have to make sure you do that without collapsing, because once you collapse it, it just becomes a solid block. Solid block will have the same convection properties as a normal block, so it won't be a very good insulator. Now the polymers that we choose, which depending on your requirement, depending on what you are doing for, you can make it out of anything. Some people have successfully made it out of eggs. Yes, you heard that right, out of eggs. It can be made. It's not a magical technology. It can be made. It's just that removing that safely and without destroying the polymers itself is the tricky part. That's the structure aspect of it. And nature have hundreds of these structures, but generally they are fulfilled. You have to make them void. Now how do we manufacture this magical thing? Well, step one, you build the gel or jello however you want to do it, or you want to extract it from nature, or you want to make your own, you go ahead. Then you do liquid exchange. Now generally liquid exchange simply means you take water. If water was used, you remove it with something else. For example, methanol or alcohol can be used. Now then you come to the most expensive and the interesting part. You put it, or there are two options you generally have. You freeze dry it, basically give the fluid that is trapped inside a way to go outside without damaging the structure. Freeze drying can allow you to do that. Or you do supercritical drying. What does that mean? That simply means you put it inside liquid carbon dioxide. Now why liquid carbon dioxide? Because it's a liquid, it will go inside. But here's the, you can do it in such a way that it behaves like a gas. You're like, what the hell? Because if you take liquid carbon dioxide, which is under very high pressure, you heat it up, you put it into what we call supercritical state. Supercritical state, the liquid is there but is behaving like a gas, so it will literally go in and out of a material without collapsing the structure. Because all you have to understand is the capillary action is your enemy here, and almost every liquid, specifically water, has a very strong capillary action. That's how like tree starts to drink water from the ground. So and you can see a very low level example of that. Take any fruit, put it in a freezer, water is leaving out, but the fruit will start shrinking. That's what is happening. The structure is collapsing. To make sure that structure is not collapsing, you want a way for liquid to go out. Basically you put liquid in there to maintain the structure or to build the goddamn thing. Then you replace the liquid with something that you know you can remove in supercritical drying mode or freeze drying mode, and then you put something pushing it out, drying it out, or whatever you want to do, but you have to do it such a way that it does not collapse the structure. So to achieve that, supercritical drying allows that, because you can take carbon dioxide and be like, okay, I'm gonna put carbon dioxide in a pressure where it's a liquid but behave like a gas, so it can go in and out. Basically you are washing it, so to say, and tada, you have a structure that is not collapsed. That is the most critical aspect. You must have a chaotic structure left behind. So that's how we do that. That's the whole end game. Everything before this point, it's a normal chemistry stuff. If you are even basically good with chemistry, you can do this. This is not a magical thing. But the moment you go into supercritical drying or freeze drying, at this point in time, it goes from science to art, so to say. So removing liquid without capillary action, that's the end game. That's the whole point. That's why it goes from 10 rupees a kilogram to million rupees a kilogram. So what is the problem with this perfect insulator? Well, it's just air, and that's awesome because air is trapped. It's not free flowing air. It's very awesome. Everything is amazing about it except the part that is strong. You can put a 1 kilogram brick on a 2 gram aerogel, so it's surprisingly strong. However, it's brittle as hell. What does that mean? That means you drop it, it shatters. And the moment it shattered, the crack basically created a perfect gap where you have perfect conductor in your insulator. So flat out, the moment you shatter it, it loses that property. Again, depending on how big the crack is, but that's the whole point. And if water touches this puppy, the end, game over. It will go inside and you have to do, basically you have to remake the goddamn thing. So think of it this way. Many users of insulation is in home insulation, but again, rain happens. It's a real thing, it happens, and you want to make sure that even if your insulation get dried, it will dry off over a few days, but it will happen. Here is done, game over, the end. If water gets inside, it will not come outside without destroying it. So flat out, water is very destructive to it, and making it is very complex, because till this point, whenever you are thinking about actually making the jello and all that, we make that in a kitchen, so it's normal, nothing fancy about it. The moment you're like, wait a minute, what do you want to do with carbon dioxide? You want to make it into a supercritical state? Yeah, I'm out, because there are very few things that can handle that kind of pressure without self-destructing. And similar thing happens with carbon fiber also, because carbon fiber, when you look at it, is not that expensive. Then why the hell the cars that are made out of carbon fiber are so expensive? Simply because when you take the carbon fiber, remove the human labor cost of actually laying it out and gluing it all together, remove that, you still have to put all that puppy, a huge car, basically into an autoclave. That autoclave is there as like a chamber which is super heated and super high pressure. That is the expensive part. That makes the carbon fiber very expensive. Same happens here, only much more difficult, much higher psi to deal with, especially in carbon dioxide. So that's the whole point. That's why it's so expensive to make. And even once you made it, you can like literally be guaranteed, like if somebody sends you like one slab of it, there's a very guaranteed charge. It will be shattered by the time it reaches you. Packaging this puppy is very difficult. So what are the developments that are being done on this? Well, raw silica aerogel is not that useful. However, be mindful, it's the most best in case of insulation wise. Like if you want the raw awesome insulation, is like I have fire on one end and I don't want any amount of energy touching the other parts. Like basically, let's say you have metal furnace and you have metal furnace control equipments that are electronic, and you want it to be close enough so it gets like proper readings and all that. You can do that. If this puppy is like, I got this, heat will not pass me through. It's awesome, but it's not that practical. So changing the core structure is possible. You have to have long polymers. Silicon makes them, but also carbon makes them, and carbon nanotube can be used, or cheaper one, carbon graphene can be used. So graphene aerogel does exist. It's a real thing, and it almost matches the same principles of silicon, basically silica aerogel. So flat out, many people have started to pour money into that puppy, and this is a bit more stable. Now, changing the core structure also allows you to get some properties. One of those amazing properties is water repellent. If you're familiar with the basically Veritasium video, he shows like he has that, and somehow he can walk inside a swimming pool and does not have a single drop of water, because on a molecular level you can design your chemical compounds in such a way that water atoms, basically complete H2O, does not come near it. It's like, bro, no. So if you do it on a molecular level, your whole structure becomes hydrophobic. Flat out, water cannot touch you. So that can be done. That makes it awesome for some application. And some other application where you are more practically thinking about it, you want it in a fabric. So basically, this is a roll of aerogel rather than like a disc like a structure. You have disc as in a like plate like structure. You have like, okay, this is a roll, wrap it around your building, wrap it around your pipe, wrap it in your car insulation, all that. Awesome. So that can be done. Fabric with fabric can be made. However, every time you change the structure, every time you mix some things, every time you collapse the air volume, of course, you are making it into with like fiber. So, and that fiber is giving you the main strength. That means that fiber is the core component rather than the air. So you do lose the insulation aspect of it. So give you a rough example. If best case scenario, aerogel would be 10x better than anything you have, by the time you make it into a fabric or something real, as in a product that people can buy, it would have come down to 3x. Now, is that good enough? Well, it would be if it was not 10 times more expensive. Keep that point in mind. That is very critical. So what we can expect in the future? Well, it's already used in space mission. They can afford the price. And for example, one of the most unique use was take aerogel and fly it through the comet tail. Now you have to understand the comet tail, and you are talking about a probe that is going through a comet. Relative velocity would be ludicrously high. So for example, for this mission, they were talking about 6 kilometers a second. Here's the deal. You put a metal box there and run it through that particle. Yeah, that particle will be annihilated the moment it hits a solid object. So aerogel is the only way that can trap it without destroying it. So they use that. And many times Mars has rovers. Those rovers have electronics. Believe it or not, electronics do not like to be very, very cold. Specifically batteries. They are like, nope. Electronics you can design in such a way that it can run off liquid nitrogen or something like that, but you cannot design the same with battery. They need a minimum temperature. So to make sure those puppies do not freeze dry themselves, you have to use aerogel. It's surprisingly light. It's mostly air, and it can be done for surprisingly effectively. So it's been used in space industry for a very long time. It's a normal thing. It's used regularly. But the new basically common use is oil pipes. So many times you have known that there are basically oil rigs that are in the sea. Now they basically drench up the oil, from oil well, but you have to pump that puppy to shore sometimes, because it's so close that it's not worth to have an oil rig going back and forth, and so far that just can't throw it. You have to have a pipeline that goes through sea surface, but because of the viscosity of the oil, they have to heat that puppy up, otherwise no pump can pump it. Now, okay, you heat it up, you are pumping it through, but here's the, you are pumping through sea. Basically, it's going through conducting system of water, and that water, basically surface level sea water, could be like, as in below bottom surface, could be as low as 3 degrees Celsius. Basically, you are cooling that puppy, and nothing will remain hot at that point in time. So what they have is a small pipe which has heated oil, then they have insulation around it, then they have another big pipe as acting as a final system. So they have pipe in pipe. Now, because of the complexity involved in that, if you phone them up and it's like, bro, the amount of insulation you have right now, let's say in diameter is 3 inch, we can reduce that diameter to 1 inch, and it will cost you 10 times more. They will like, shut up, take my money, give me the goddamn magic technology. And that's what we do right now. Like, it's very like, it's a magical scenario, because the moment you reduce the diameter, you reduce the cost of the pipe by a very large fraction, and the cost of laying down that pipe goes down by a very large fraction. The amount of boats you need to carry to lay down that pipe goes down drastically. So because of that many drastic reduction, it's like people are like, dude, even if it was 20 times more expensive than normal one, we're gonna pay it happily and still make profit out of it. So that's his like killer use. Another industrial insulation also happens. I specified metal furnaces and all that, just where you want to make sure the hot side is hot and cold side is cold. You can utilize this puppy. Another aspect is cryogenics, specifically because again heat goes in only one direction, hot to cold. So what if you want to make sure the atmospheric heat does not go into your cryogenic liquids, let's say liquid helium, liquid basic, not helium so to say, basically liquid methane, liquid oxygen, liquid nitrogen. These things are generally used in rocket systems. But again, to pump them around, you will have to deal with what we call boil off. Basically, atmosphere is gonna boil it off. You don't want that. That's a loss of propellant, and B, serious hazard, because if that boil off happens in the wrong place, boom. So aerogel has been used a lot, so it's a real thing that people are using it, because again, we built it quite early, long ago. So it's a real thing, real product. However, because of the ludicrously high cost, it's not justifiable for average Joe, so to say. For you and I, it's not that justifiable. So I do not see the chance of like, oh, this winter vest is made out of aerogel. Yeah, some people may buy it same way. There are some modern bags that are made out of Kevlar, but it's not normal use, so to say, because of the cost is too damn high. And by the time you make it useful, it's not that magical. It's no longer 10x better, it's like 3x better. So you might be like, or I can just put 3 times more of that. So people generally go with that normal structure. Thankfully, this is human safe, so it's not like it's dangerous as carbon nanotube. So future is very bright in terms of industrial use, but do not expect this to be your next winter vest. So this was my presentation on aerogel. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me your disappointment. Please leave a comment, because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.